last but certainly not least, we have another speaker lined up, and this is Lenny Lobel. I'm not even sure if we need to introduce Lenny. He has been he has been around for such a long time, Lenny, a long time MVP. For how long have you been an MVP, Lenny?
It's coming up on a decade now, Thomas.
A decade now. Wow.
Yeah, nice to see you.
Nice to see you too, Lenny. Lenny is also the CTO and founder of Slick Technologies, based out of New York, major contributor for multiple Azure data services, SQL and Cosmos DB included. The topic for today, Lenny, is a topic that I think never gets old, is data partitioning and modeling, right?
Indeed.
Yeah.
All right, so, well, thank you so much. And it's great to see you all here at our first ever Azure Cosmos DB conference. My name, again, is Lenny Lobel. I'm a data platform MVP. As Thomas mentioned, I've been working with Cosmos DB since the document DB days back in 2014. And I'm here today to talk to you about data modeling and partitioning in Cosmos DB. We all know that partitioning is very critical, so we're going to be talking quite a bit about that. Of course, Cosmos DB is many things. It is horizontally scalable, it is non-relational, and a bunch of other things. It's we can define it as being globally distributed, multi-model, tunable consistency. There's lots of ways you can describe Cosmos DB, but for the purpose of this session, let's just focus on these two definitions. It is horizontally scalable, and it is non-relational. And drilling into both of those, when we're dealing with Cosmos DB, right, we're dealing with a container, and we interact with one container as a single logical resource for storing documents and retrieving documents. But of course, behind that container, there's a cluster of servers, right, if you will, or physical partitions, for lack of a better term. We'll just think of them as physical machines, just like a box that has storage and CPU processing power. And there's been no real upper limit on the number of servers or physical partitions in a cluster behind a container. And therefore, if you partition your data model properly, there's really no upper limit. You have unlimited storage and unlimited throughput with this model, right? Because each physical partition offers more and more storage and throughput. Right. What was the other term we were going to drill into? Non-relational. And if we think about how we do things in the relational world, where we're dealing with tables and rows, what is it that we love to do more than anything else in this world, right? We love to join these things, right? That's what makes us happy. We like to come up with the perfect normalized data model. We like to craft our entities such that we have primary and foreign keys, giving us a very normalized relational data model. And that's the way things work in the relational world. But of course, in Cosmos DB and in the NoSQL world, we are storing data inside of JSON documents, not rows. And while there's certainly nothing you can store in a row that you can't store in a JSON document, and therefore nothing stopping you from designing a data model where you pretty much, treat JSON documents as if they were rows and have, references from one related document to another. While you can do that, such a design would break down in Cosmos DB. This would perform very, very poorly. It could be made to work, but it could not be made to work well. And why is that? It ties back to our first definition of being horizontally scalable. And the fact is that any one of these documents can land on any physical partition. And in order to maintain the supreme level of performance, the high performance SLAs and the single digit millisecond reads and writes and all of those guarantees on performance, it's simply not practical or feasible to enforce relational constraints between related documents, or indeed to even support joins on them. And that's why we need to think about things differently. Because of course, after that opening, it certainly begs the question, well, then is Cosmos DB at all suitable for a relational workload? And the answer is, of course it is. Otherwise, the session would be very short. It would end here and I would go home. But in fact, many workloads are relational, not all. But many are, and Cosmos DB is certainly suitable for those relational workloads. It's just that you have to think about things differently. You can't do things the way that you've become accustomed to doing them in the relational world, even if some of those tried and true practices have been around with us for decades for some of us. We have to kind of go against the grain of what we consider to be best practices in the relational world in order to materialize relationships in an efficient manner in this non-relational world of Cosmos DB. And so with that kind of backdrop set, let's just have a look at this this little diagram here. This is our Webstore relational model. Think of this as a database behind our customer-facing e-commerce website. And it's a relational workload, like a mini AdventureWorks. It's got all the things you would expect to find in a typical relational data model. We've got customers with a one-to-many relationship with their addresses, a one-to-one relationship with their password. We've got products, which participates in a parent-child relationship with product category as well. There are product tags, in which case we've got a many-to-many relationship here. So there's that intermediate table, right? This intermediate product tags table here. Just trying to get my laser pointer to work, right? With foreign keys pointing to both sides of the many-to-many relationship. And we've got sales orders, right? Which are children to customers. So a customer will have a set of sales orders. Each sales order will have a set of sales order details. And it's a small data model, but it is fairly representative of the most common data modeling patterns that you'll find in a relational database. So if you're coming to Cosmos DB fresh and you're just, and it's new to you, your first instinct might be to say, hey, I've got 9 tables here. Maybe I should have 9 containers, right? One container would make sense to store, to think of a table as a container when you're first entering the world of Cosmos DB. But the question is this a good design? And of course, the answer is no, as I started explaining, that due to the lack of joins and the fact that there is no referential integrity and there are no relational constraints, this could be made to work, but could not be made to work well. It would perform very, very poorly. It would be actually the worst possible design that you could come up with. So for the rest of the session, we're going to take it step by step and see how to implement a data model like this in Cosmos DB for high efficiency, high performance, and high scale. And we'll start with customers. We've got 3 tables here for the customers, the one-to-many between customer and addresses, and the one-to-one between customer and password. Step 1 is you just literally translate your column names to property names as if it were a JSON document, which is all I've done here. Other than camel casing the identifiers, the property names in my JSON document match the column names in my database. I had to rename the primary key columns simply as ID because, of course, in Cosmos DB, that ID property must always be named ID. But otherwise, it's a simple translation forward. And at that point, I could stop there, right? Because I do have these kind of, and I don't want to use the word relationships here. Let's just say references. I mean, I do have IDs pointing from one document to another. But let's just call them references, not relationships, because this is a non-relational data model. And so it begs the question, would it be better, perhaps, since we are working with JSON, and JSON is a semi-structured document format, we could embed our addresses as an array, as I've done here. I only have space to show one address, but those square brackets mean I could have any number of addresses. Well, let's say a reasonable number of addresses, as we'll get to in a moment. And the password itself is embedded as an object using a curly brace. And, thereby, you eliminate the problem of no joins if you pre-join, right? We have pre-joined, effectively, our addresses with the customers and the password of the customer. And we've also solved the problem of referential integrity because the child array lives nested within its parent and can never be broken from its parent, right? So the question is this appropriate to do this? So do you embed or like so, or do you reference like so? And you need to, this is a very typical question that you'll ask during this process. So the rules aren't hard and fast, but the general rules are, if you've got a one-to-one relationship like we have in the case of a password, or a one-to-few relationship like you have in the case of addresses, then it would be reasonable to embed. What is one-to-few? If in the relational world, there's no such thing. It's either one-to-one or it's one-to-many. And even if it's 2 or more, it's considered one-to-many. In this world, we are thinking of a data model where we have a JSON document with an upper limit size of 2 megabytes, where it's perfectly reasonable to cap the number of addresses that a customer might have in their profile to all fit in 2 megabytes. And so it would make, that's a one-to-few. Think of their orders. We want to think of orders as one-to-many, don't we? We want lots and lots of orders, ideally unbounded number of orders. And so it's certainly not feasible to embed all of that in a single document. And so then you'll reference. When it's a one-to-many relationship, particularly unbounded relationships, you'll go with referencing. Or if you have a many-to-many relationship, as you'll see the way we'll handle the product tags relationship, you'll also want to reference, or actually a combination of embedding and referencing. And another kind of general rule is that, even if it's just one-to-one, and even if it's or just one-to-few, if you're never really querying for these things together and you're never really updating them together, it also makes sense to reference them. If they're being queried or updated independently. Again, these aren't hard and fast rules, but for our scenario here, we can certainly go with embedding for the addresses and for the password and turn 3 tables into 1, essentially, by encapsulating all of that information in our customer entity. And then the question at that point becomes, if we're going to store customer documents like so inside of a customer container, how do we partition that container? What is our partition key? The most critical question that you'll always have to ask when defining a container. Well, the way that you come up with the right partition key is you need to really understand the most common querying patterns. You need to understand how your application is going to most frequently query your data, how your users are going to most frequently query your data. And again, sticking with this scenario of a customer-facing e-commerce website, the most common query is that a customer is going to want to retrieve information about their profile information, which is their name, address, all their addresses, their password, perhaps for rendering on a profile page. And so the most common query is really to get an individual customer by their ID, which would pull in their addresses, right, because they're embedded, and their password because it's embedded, right? And so that really means the ID property itself would be actually the most suitable property for the partition key here. Now, it might seem like a strange choice because, as you may or may not know, every document is unique in a container based on a combination of this ID property here and whatever other property you decide to choose for the partition key. However, if you choose the ID property itself as the partition key, then you get exact uniqueness of 1 document per logical partition, and you can't have more. Now, again, it might seem like an odd pattern, but it is actually a very good approach when you're dealing with point operations, point reads and point writes, where your primary use case is to read or write an individual document at a time. The ID property is often a very good choice, and it certainly satisfies our most common query, so that's what we'll go with. Now, let's plow ahead with our next entity in the data model, which is product categories. This is very, very simple. It is really just a key value pair, right? There's a product category ID and a display name. So, like before, we translate our column names into JSON property names, and then decide to put that in a container for the product category. We'll put that in the product category container, ask the same question, how do we partition it? Answer it the same way. What's your most common querying pattern? On that website, you're going to want to display all the product categories, right? Maybe in a sidebar on the left or a little menu, so that the user can click a product category to drill in when they find a category of interest to see the products in that category. And that really means a select statement with no where clause because you want them all. And the way that you implement this type of pattern in Cosmos DB is to add a type property. Really, I want all of them inside 1 logical partition. Think of this as a lookup list. Anything that's of reasonable size, and when I say reasonable size, I mean it'll fit inside of a single logical partition, which is limited to 20 gigabytes in size. And we certainly don't have a list of product categories coming anywhere near that. So there's no problem at all putting them all inside 1 single logical partition. And the way we do this is we add a type property, which is certainly optional. It's schema-free. You're free to define any schema. The ID property is the only required property. But it's always a good practice to throw in that type property to help unambiguously distinguish one type of document from another. And if you create a property called type and you set the value of that property to category for every product category document, and then partition on the type property, of course, that's going to lump all of them into 1 logical partition and give you a very efficient result, a very efficient query that results in returning all of the categories that you have in the database, all in a single partition query. Product tags, I won't rehash that because it's the same concept. A simple key value pair where the user might want to see a list of tags. If they see a tag of interest, they'll want to see all the properties associated with that tag. Same concept. Translate the column names to property names. Put them in a tag container. Ask yourself how to partition it and answer it with the same answer. We want to get all the product tags. It's a select statement that returns them all. So we'll add that type property only for the tag documents. We'll set the value to tag, right? And then by partitioning on the type property, all of the product tag documents are stored together in the same logical partition, just like categories. Products is where it gets more interesting. With products, we have that many-to-many relationship, right? So first we'll do step one, we'll translate our column names to property names. But what about this many-to-many relationship with product tags? The way this is implemented, and I mentioned this earlier, is with a combination of embedding and referencing. I am embedding an array of tag IDs into the product document, but that array itself is an array of references to tags. And in this case, I am embedding an array of tag IDs into each product document. This could also be made to work by embedding an array of product IDs in each tag document. Depending on your usage patterns, one of those may be better than the other, but in either case, this is how you implement a many-to-many relationship. Now, how do we partition the products? We're sticking with our e-commerce website scenario, the user has found a category of interest. They want to get all the products in that category. So the most common query for products is going to be get all the products within a given category, not all the products in the entire database. So that means we want all of our product documents to be kind of grouped together logically in a logical partition by category, which you guessed it, if you were thinking category ID is the proper property to use here, you guessed correctly, and that will achieve just that. So now I've got my product documents in hand, but if you look at a product document, what do you have inside of a product document? You have a bunch of IDs, but you don't really have everything that you need to display the product on your web page, right? You have the category ID, but not the category name. And you have the tag IDs, but not the tag names, right? And that means that if you want to get all the products in a given category and display them on your web page, you would have to run one query to get all the products in a given category. This would be fairly efficient because it's a single partition query. You could even further filter on this within a category if you wanted, and it would still be a single partition query, but you don't have the display names. So it would be a second query now on the category container by the category ID to get the display name for the category, and then it gets worse because for each product returned by that first query, you would need to run this third query on the tag document to get the display names for the tags. And this is where, you know, you pound your fist on the table and say, well, where are my joins? Of course, in the relational world, this is a no-brainer. You just join these things together on the IDs and you get the display names, but we're in Cosmos DB world. There are no joins. We need a new way, a different way of handling this. And that is going to be done with de-normalization. We're going to simply copy or duplicate that master data in each product document. So each product document, in addition to having the category ID, will have a copy of that category name. That's a copy of the master data. The tags property is now not just an array of IDs, but an array of objects that includes both the tag ID and a copy of the tag name, again, from the master data. So at the point of insert, when I create a new product, I'm also copying that master data for the category name and the tag names, which is great, meaning when I have a product document in hand, I have everything I need to display my product on the web page. But of course, the obvious question becomes, what happens when there's a change to that master data? Somebody comes along and changes a category name or a tag name. And so what we really want to do is listen for changes on those two containers and cascade them to the product container. And that's where the change feed comes in, which is a very critical component of Cosmos DB, a bit of the unsung hero. You don't hear enough about it, but it's what drives a lot of microservice architectures. The change feed gives you a persistent log of changes. So every time a document is added or modified or changed in the container, it gets emitted through the change feed in near real time, and also persisted to the change feed, so it can always be rewound and replayed. And you can build microservices. You can use Azure functions to do this very easily, to watch the change feed, respond to every change that occurs, and respond and process it in some way. And in this case, it would be to keep our de-normalized data model in sync with master data as it changes. So on the product category container and on the product tag container, they each have a change feed. And when any master data changes, we can have an Azure function wake up and cascade the change to the product table. Here's just some pseudocode. Here's my Azure function name. The Cosmos DB trigger attribute means the Azure function will wake up whenever there's a change to the collection name, which is the container name. That's the product category right here. That's this guy right here on the left that we're watching for changes for, this product category container. And we're handed a read-only list of documents that have changed, and we simply iterate them. And for each one of these represents a change, let's say to a product category. In this case, we will just get the category ID and name. And now we'll need to update each product to cascade and propagate that master data change. And that's done first by querying for all the products in that category very efficiently, again, because we're partitioned on the category ID. So this will return all of the products in one efficient single partition query, and then set up our iterator to process those results and update them one at a time, replacing them with point-right updates. That takes us to our last set of tables in our data model, which is our sales order and sales order details. By now, the process should seem a little bit familiar to you. Step 1, translate column names to JSON property names. Step 2, ask the question, embed or reference. Is this one-to-many or one-to-few? Well, hopefully our sales orders are large, but I still think that at 2 megabytes, we can accommodate even a large sales order. So we would definitely be better off by embedding the details. Right, so we'll embed the sales order details, essentially pre-joining them. And they're embedded there as an array of details inside each sales order document. And then we're going to put them in another container called the sales order container. Ask the usual question: how do I partition this container? Well, answer by re-asking the usual questions. What are my most common queries? Well, we've got this very common query, again, that the customer is going to be running. All the customers visiting your website are going to be frequently asking to see their sales orders. And then perhaps less common query that might occur, let's say, in the back office by some executive who's looking at a dashboard, perhaps, who wants to see their best customers, might want to query for all the customers, descending by order count to get their best customers at the top of the list. So let's go with the common scenario first. Getting all sales order for a customer would look like something like so. That means that's how the query would look, right? Give me all the orders where the customer ID matches this customer. So if we partition on the customer ID, it'll do just that, right? It'll put all the sales orders for customer A in its own logical partition and each other customer in their own separate logical partitions. I could get all the sales orders or a subset of the sales orders from a customer with a very efficient single partition query. So that means customer ID is the correct, is the appropriate partition key to use here. But now let's slam on the brakes here and pause. And remember, I promised we'd come back to the customer container where we partitioned on the ID property, because that's the same value that we're partitioning on. We're partitioning on the customer ID in both cases. In the case of the customer container and in the case of this sales order container, we determine that customer ID is the appropriate value. Now, granted, it's called ID in the customer document, and it's called customer ID in the sales order document, and we'll iron out that wrinkle in just a moment. But the value is the same. It's the same value that we want to partition on. And when you want to, when your partitioning needs are the same between 2 different types of document types, you will not create 2 different containers. We are in a schema-free world here in Cosmos DB. There's no rules on schema. There's nothing preventing you from storing 2 different entity types in the same container. And in fact, it's encouraged to do so when you have 2 types, even though they're different types, when they share the same partitioning needs or they share similar throughput needs. Those are reasons for storing multiple items of the same type in the same container. And that applies here because we have the similar partitioning needs on both these entities. And that's the customer ID. So what we'll do is we will not create that new sales order container. We will stick with the single customer container that we started with. We'll just have to make a minor adjustment since the ID property in each of these 2 types is different. In the case of the customer document, the ID is the customer ID. In the case of the sales order document, the ID is the sales order ID. And it's the customer ID property that's kind of a foreign key, if you will. So we'll fix that with another tiny little bit of denormalization. We'll throw in a customer ID property on the customer document and essentially store, 2 copies. I guess I didn't have that call out in there. We will store 2 copies of the customer ID. The customer ID will be stored both here and here. And it's the same name property now in both documents. And so I can partition on the customer ID property. It's definitely, I mentioned, a good idea to always have a type property, but that's especially true when you are combining types in a single container. You want to unambiguously distinguish between 2 types, especially when they're in the same container. But now that's our data model. At this point, we now have logical partitions where we're mixing types. One document in the logical partition for customer is the customer document, which, remember, embedded inside of that are the addresses and the password. And all the other documents are sales order documents, and remember that embedded within those are all the sales order details, and all of which are contained in a single logical partition per customer. So this is a very nice little design for customers and sales orders. I can run a query like so to get all the sales orders for a given customer by querying on the type property for a given customer. In fact, if I left out the type portion of my query and I just got all of the documents for a given customer, it would give me the customer and all of their sales orders along with all of the embedded information with a very efficient single partition query. And so that therefore we are getting around the issue of there being no relational integrity, no referential integrity, no relational constraints, no joins, because you see it's kind of all joined together for us here, isn't it? Because we partitioned properly, so our documents kind of join together naturally in an efficient manner through single partition queries. And within those documents, we've got pre-joined embedded data as well. And we've kind of like dealt with these radical differences between the relational world and the non-relational world. And that takes us to our very, very last query example, which is that exec sitting in the back office looking at their dashboard who wants to see their top customers. Again, in the relational world, it's a no-brainer. You just do a select count on that order table, group by customer ID, and you're done. That doesn't work here. So what we'll do is another little bit of denormalization. We'll throw in a new column called a new Freudian slip there, a new property called sales order count. And we're going to maintain, we're going to not duplicate data in the sense that we're going to duplicate the count. So if there are three sales order documents here for this customer, then the number 3 will be stored in the customer document as well. And that means that if I want to add a new sales order for customer A, I also need to update that customer document to increment the sales order count. How can we do that? If you're thinking change feed, you're definitely on one right track. Change feed is a wonderful mechanism, but in this case, I'm going to do one better because everything is in the same logical partition. We can take advantage of transactions using a stored procedure. Now, this is in this case, it's a stored procedure with JavaScript. It can be done in C# or other languages, well, I think at least in C# using transactional the transactional batch feature. But in either case, what we're doing here is just a little bit of code that is going to retrieve the customer document, increment the sales order count of that customer document, and then replace it, although that replacement occurs in the context of a transaction and is not actually committed until this JavaScript code completes successfully. So it's been written to the container but not committed. And then we can create the new sales order document and return, let's say, the new count because we want to return something, but only then when the function completes successfully, does everything get committed, the new order is written, and the customer document is updated all at the same time. And once you've got that store procedure in place, it does mean that anytime you want to add an order document, you must do so by calling the store procedure and not by just dropping it in by directly inserting it. And if you follow those guidelines, you will always be able to run a very efficient query like so, relatively efficient query. This is a cross-partition query, right? Because there's no where clause in here. We're ordering by the sales order count descending. Is that evil? It's not evil if it's in the minority of cases, like this one exec sitting in the back office who's hitting refresh on their dashboard once an hour. It is evil if it's the customer-facing website with all of your customers hammering away with cross-partition queries day in and day out. That is when cross-partition queries need to be avoided. But here it's perfectly fine. And it's relatively inexpensive because the sales order count has been pre-materialized for us. So to wrap up, with 2 minutes to go, our final design, we have a database with these 4 containers, not 9 containers, 4 containers. And in the customer container, we've got 2 different types. And in the case of customer sales orders and products, we're also embedding to cut down on the number of containers. And if you've been paying attention, and I know you have, you're probably thinking to yourself, product tag and product category, they're both partitioned on type. They're both small lookup lists. Doesn't make sense to create a container per small lookup list. We could combine those into one, let's say, metadata container called product meta, and combine product tag and product category documents, and now bring it down to 3 containers with a very efficient data model to handle a relational data scenario in a non-relational database like Cosmos DB. The key takeaways for this session are: you really must know your key patterns, your key access patterns, how your database is going to be most frequently queried and written to as well, and you design for those patterns. To state the obvious, partitioning is critical. You're not going to achieve that performance and scale if you pick a poor partition key. You want uniform distribution as much as possible, both for storage and throughput. Using these techniques that I covered to materialize relationships either by embedding or by referencing through denormalization, pre-aggregating, combining multiple entities, different entity types in the same container if they share similar partitioning needs and they share similar throughput needs, and using your choice of either the change feed or transactional integrity when the updates are within a single logical partition using stored procedures as well. So I hope you enjoyed the session as much as I enjoyed preparing it for you. I want to thank the team for inviting me to speak to you today, and throw it back to you guys for questions if you have any.
Thanks, Lenny. This was an awesome session. I really love the way you graphically lay out those design considerations. It makes it so much easier to understand, how to tackle those kind of exercises.
I had some good inspiration there, Thomas.
Yeah, well, you presented very, very well, and I hope this is going to help any of our viewers who will need to tackle such a design exercise in the future. We are at time and we are short on time again, but I just wanted to relay one question we got from the many questions we got on the chat. One of our viewers was asking, should multiple microservices use the same Cosmos DB container?
Should multiple microservices use the same Cosmos DB container? So that's an explosive question. Pandora's box with this. I kept things very simple here. Sometimes you can't just settle on one partition key, and you'll need a microservice to actually replicate data from one container to another. Just because you have heavy querying patterns where half the time one property is suitable as the partition key, the other half the time another property is suitable as the partition key, then you're going to have one microservice whose purpose in life is to just keep those two containers in sync. And then you will almost certainly need or want to create materialized views for queries that would otherwise be very expensive. And that involves more microservices to create materialized views in yet other containers. So you are talking about multiple containers and multiple microservices. So although all those microservices could all be consuming the change feed of a single container, which is a really nice design aspect to the way microservices can be implemented. You can have a microservices architecture where you've got microservices that are completely independent from one another. They're all sharing the same change, they're consuming the same change feed and maintaining state independently of one another regardless. So it's a mix and match. It'll depend on your scenario, but it'll almost always involve multiple containers and multiple microservices.
That makes sense. Thanks again, Lenny. We couldn't have our first Cosmos DB conference without you. So we really appreciate your participation here.
Of course. And thanks again, everyone, so much for tuning in. So it's been a really great live stream. It's always great to see how our customers, our partners, and our community are building their applications with Cosmos DB. Just wanted to check in, Tim and Thomas, did you have any interesting takeaways or insights or things that you wanted to share that you've learned from what we saw today?
Tim?
I really enjoyed Lenny's session. That was awesome. I mean, as somebody who knows a lot about Cosmos DB, it was great to see a lot of tips and tricks that even more advanced users could really use to become a power user of the product. But thank you for watching today. It was really great to have you as viewers. In addition to these great sessions in our live stream, we have 18 on-demand sessions that you can watch at any time. So to see this great lineup of on-demand sessions, you can visit gotcosmos.com and click on On-Demand Sessions. You can also join us for a weekly podcast where our host, Mark Brown, will meet with members of the Cosmos DB team each week and talk about things relating to Cosmos DB, like querying, change feed, analytics, anything you can do with Cosmos DB we'll cover on the show. For the show schedule and upcoming episodes, also, you can go to gotcosmos.com/TV and you'll be able to view all of that there. And finally, if you're new to Cosmos DB and want to find new ways that you can try it for free, read our blog post on the 4 ways that you can try Cosmos DB for free. That'll be available at aka.ms/cosmosdb-free. You can catch our next stream for the Pacific time zones starting in 8 hours. That'll be at 8 p.m. Pacific time, and 11 p.m. US Eastern Time. And thank you again for joining. It was so great to have you with us for the first part of the Cosmos DB conference.
Thank you all.